This video is about finding derivatives of inverse trigonometric functions. Before we get started on finding the derivatives of inverse trig functions, we should probably refresh our memories about sine, inverse sine, and inverse cosine. So I'm not sure that you remember, but the range of inverse sine is minus pi over 2 to pi over 2. And the domain is minus 1 to 1. We can find the derivative if we start with the expression that represents the inverse function in the other order. So rather than saying what angle has a sine of x, well, that angle is equal to y, we say sine of y is equal to x. So we're going to start with x equals sine y, and we're going to differentiate implicitly. So the derivative of x with respect to x is 1, and the derivative of sine is cosine of y times y prime. So now we can rewrite this y prime is 1 divided by cosine of y. Well, we happen to know that sine squared y plus cosine squared y is equal to 1. So we could rewrite cosine of y as the square root of 1 minus sine squared y. And if we go back to our original expression, sine y is equal to x. So we're going to get 1 divided by the square root of 1 minus x squared. So in summary, the derivative of the inverse sine of x is 1 divided by the square root of 1 minus x squared, as long as x is between negative 1 and 1, which is the domain of your inverse sine. So let's take a look at a couple of examples. In this first example, we want to take the derivative of the inverse sine of 3x squared minus 5. So using the formula above, we're going to get 1 divided by the square root of 1 minus 3x squared minus 5, and then we have to apply the chain rule. So the derivative of 3x squared minus 5 is 6x. For our second example, you should notice that this piece in here is the derivative that we just found. So to find the derivative here on the right, we have a chain rule twice. Our outermost function is cosine. Our second one is inverse sine, and the innermost one is 3x squared minus 5. So we'll take the derivative of those in order. So the derivative of cosine is negative sine of the inverse sine of 3x squared minus 5. And the derivative of the inverse function we just found over here is 6x over the square root of 1 minus 3x squared minus 5 squared. Now, we're going to look here at the sine of the inverse sine. Well, the sine of an inverse sine of a function is just that function. So our final result here is going to be negative 3x squared minus 5 times 6x divided by the square root of 1 minus 3x squared minus 5 squared. We can follow a similar process to find the derivatives of all of the inverse trig functions, but I want you to pay attention to a couple of things. The co-functions, the derivatives of the inverse co-functions are opposites. So for example, if the derivative of inverse sine is 1 divided by the square root of 1 minus x squared, then the cosine is going to be the negative of the derivative of the inverse sine. Similar for tangent and cotangent, and secant and cosecant. So all of your co-functions, the ones that actually say cosine, cotangent, cosecant, will be negative. So basically, if you learn the first three, sine, tangent, and secant, then the other three basically are free. You just have to remember that the co-functions are negatives. So let's take a look at some examples. We've got the first one, the derivative of the inverse cosine of x squared minus 5x. Well, we just learned that should be negative 1 divided by the square root of 1 minus our argument, x squared minus 5x, quantity squared, and then we have to take the derivative of that argument, which is 2x minus 5. So our final result would be the negative 2x minus 5 and the square root of 1 minus x squared minus 5x squared. This one's a little more complicated. We have an inverse secant and a natural log of x. So the derivative of the inverse secant is 1 divided by the absolute value of the argument times the square root of the argument squared minus 1. And then we have to take the derivative of this argument. Well, the derivative of the natural log of x is 1 over x. So our result here would be 1 divided by x times the natural log of x times the square root of the natural log of x squared, subtract 1. Let's take a look at another example. Here we have the derivative with respect to x of the inverse tan of 12x. And the derivative in general of the inverse tangent of x is 1 over 1 plus x squared. So in this case, we get 1 over 1 plus 144x squared. And then using the chain rule, we want to multiply by the derivative of that inside function, which is just 12. Taking a look at this next example, we have the derivative with respect to x of x times inverse cosine of x minus the square root of 1 minus x squared. I'm just first going to rewrite this so that it will be easier for me to take the derivative of the second piece using the power rule. So x inverse cosine x minus 1 minus x squared to the 1/2 power. Now I'm ready to take the derivative. So here I'm going to use a product rule. The first times the derivative of the secant, which is minus 1 over the square root of 1 minus x squared, plus the second times the derivative of the first, and then the power rule here, minus 1/2 1 minus x squared to the minus 1/2 times minus 2x. And we're going to notice if we do just a little bit of simplification here, you might notice over here that the 2 and the minus 2x cancel, and a negative times a negative is going to give us a positive. So we'll actually have positive x over the square root of 1 minus x squared plus the inverse cosine of x, and those conveniently add to 0, so we just get inverse cosine of x. Let's take a look at an application problem, which is one place that we might run into the derivative of an inverse trig function. So for this example, we have shadows in a ballpark. As the sun descends behind a 150-foot grandstand of the baseball stadium, the shadow of the stadium moves across the field. Let L be the line segment between the edge of the shadow and the sun, and theta be the angle of elevation of the sun, the angle between L and the horizontal. The shadow length S is the distance between the edge of the shadow and the base of the grandstand. Our first question here is to express theta as a function of the shadow length. So I'm going to draw this right triangle kind of separate from this picture. I've got the angle theta, S, L, and 150. So if I wanted to find theta as a function of S, we might first say that tangent of theta is opposite over adjacent, or 150 over S. Therefore, the inverse tangent of 150 over S is equal to theta. Now we want to compute d theta ds when S is 200 feet and explain what that rate of change actually measures. So first, I'm going to rewrite this as inverse tan of 150 s to the negative 1. That'll just make finding my derivative a little bit easier. So differentiating with respect to s, I'm going to get 1 divided by 1 plus 150 s to the negative 1 squared, so 1 over 1 plus x squared, times minus 150 s to the negative 2. So simplifying this, we get d theta ds equals negative 150. I'm going to move this s to the negative 2 down, so s squared 1 plus 150 squared times s to the negative 2, or negative 150 s squared plus 150 squared. Now we're going to let s be 200, because that's what we were asked for here when s is 200, and we will get the d theta ds is negative 150 over 62500, or negative 0.0024 radians per foot. So what does it mean? Well, this is the change in the angle over the change in S. And remember that S, this distance here, is the distance from the grandstand to the edge of the shadow. So what we're saying is, as the shadow gets longer, every foot that the shadow grows, the angle theta decreases by 0.0024 radians. Decreases because it is negative. I'll pick up with another video for derivatives of inverse functions in general. That concludes this video. Thank you.